All right, we're going to get started again. I see coffee cups, which is a good sign. Okay, so where we left off, we're talking about the nodes and antinodes of your flame transfer function and the disturbances that are driven by those. So hopefully our pipe cleaners came in handy again today. So let's talk about what this looks like in experiments. We saw very clearly in the data from Nick Bunce's thesis that you can see this, but we haven't looked yet as to what disturbances are causing those constructive and destructive interference patterns. So there are two experiments that I want to look at. The first one was work that was done by Paul Police when he was a graduate student at École Centrale. So he worked with Daniel Durox, Thierry Schuler, and Sébastien Candel. And this is a beautifully written paper on basically where that interference phenomenon comes from in a swirl stabilized flame. So just to outline what's going on here, they have methane and air that comes through. They have a swirler where they can change the swirl number. And then they have a center body inside a quartz combustor. And so you can see that the flame is stabilized on the end of the center body. And they measure the input velocity fluctuation two ways, one using LDV and one using a hot wire. They have in the past used multi-microphone methods, but for this particular study, they didn't. They looked at two different swirlers, a low swirl number and a high swirl number configuration. Having a higher swirl number creates stronger recirculation in the center and kind of a squatter flame as a result. And so by changing the swirl number, you're changing your flame shape, which we saw from Nick's data should also cause a change in the flame transfer function. So on the left are pictures of the flame A and flame B. So you can see flame A is a little bit shorter. This is just an instantaneous flame image. And these are, this is the line of sight integrated chemiluminescence image. And this is what has been processed using something called the operability convolution, which basically, if you assume axisymmetry, it kind of looks like what the plane in the middle would look like. You can tell when images have had the operability convolution applied to them because you get this weird artifact along the center line if your data isn't perfectly axisymmetric, and no swirling flow is ever axisymmetric. I've also done a lot on the instabilities in swirling flows, and I've had a lot of people come to me and be like, it's not perfectly axisymmetric. And I was like, nobody's is, it's fine. You're not doing anything wrong. But anyway, so you can see flame A is shorter than flame B. And what's being shown here are the flame transfer functions, or what they call the flame describing functions, and we'll have a sidebar on that in just a second, of the two flames. So flame A on the left and flame B on the right. You can see that the antinode here, the node, and then the antinodes differ in frequency space depending on the length of the flame. And so here this is a lower velocity flame, and this is a higher velocity flame. And so we saw that with Nick's work. You increase the mean velocity, you end up with a higher frequency for your node. So in this study, one of the things they wanted to understand, this was sort of second order important to the message today, but I do want to point it out because there's a lot of this in the literature. They changed the level at which they were forcing the flame. So this is U prime over the bulk velocity. So this is what we've been calling epsilon. And I told you before, when we're measuring flame transfer functions, which is, just go for it. It's going to make a ton of noise. Excellent. Okay. If you're trying to measure a flame transfer function, you want to stay in the linear regime, which is like 5%, right? So U prime over U bulk would be 0.05. But one of the interesting, we've talked about nonlinearities that come from the kinematic restoration and the kinematics of flames. But then there's a whole bunch of other really cool nonlinear crap that happens when you have complicated flow fields, right? And so in particular, there are a couple of studies. There was work done by Balachandran in the early 2000s and by one of my academic siblings, Ben Bellows, who just saw super weird nonlinear behavior in swirling flows that has to do with the dynamics of the flow, not so much the dynamics of the flame. The flame's just like following along to the craziness of the flow. And so that's kind of what they were looking for here, knowing that in previous studies people have seen that. And so you can see they got to really high forcing amplitudes. This is like 72% of the mean flow. Granted, the mean flow is only 2.67 meters per second, but this is a really high amplitude forcing. And so this is so far out of the linear regime, it's definitely not linear. And so you can't call this a flame transfer function anymore. Instead, we call it a flame describing function. So the flame describing function is the same basic thing as the flame transfer function, but now it's not only just a function of frequency, but it's also a function of amplitude. You still have the single input, single output configuration. You're only looking at like one frequency at a time, but now you have u prime as a function of epsilon. So now you have to measure it at a bunch of different amplitudes or calculate it at a bunch of different amplitudes so that your input is a function of epsilon, your output is a function of epsilon, and so then your transfer function is a function of epsilon. One thing that I didn't put in here, but that happens, is technically your mean flow can also be a function of epsilon. We saw this in my PhD thesis. I really freaked my advisor out. But you can acoustically force something so severely that it changes the time average. This is very common in flows. It certainly happens with flames that are just sitting in flows. And so technically in the denominator of each of these, you know, Q bar and U bar should also be functions of epsilon. I'll fix that someday. Okay, but basically everything we just talked about with flame transfer functions applies, but now you don't just have to measure it at a whole bunch of different frequencies, you then have to measure it at a whole bunch of different amplitudes. Let me tell you, measuring flame describing functions takes a long time. Okay, sidebar over. So we know that, okay, so let's go back, whoa, wrong direction. We saw really clear nodes and antinodes in these transfer functions, right? So this is just like beat you over the head obvious that there are constructive and destructive interference things happening. You must have multiple disturbances along this flame, and so that's resulting in this pattern. And one of the things that separates this study from all the others and why it has a gajillion references is because they hunted that down. So very cleverly, what they did was they measured a whole bunch of stuff. They measured two different velocity components using LDV at the output of the, right at the base of the flame. They turned this into a fluctuating swirl number. So the swirl number is nominally the ratio of swirling momentum over axial momentum. And so you can see for these, there's a pretty significant swirl number fluctuation. They measured the fluctuation in the flame angle, which is a result of this boundary condition. And then they measured the fluctuation in the heat release rate because of it. And they looked at this, they did these very careful measurements at two different frequencies. One was at 60 hertz where you got a node, and one was at 90 hertz where you had an antinode. And you can really clearly see these different velocity fluctuations lining up. And when you added everything together, your global Q prime over Q bar for the place with the destructive interference, right? Look at how out of phase everything is, was pretty low. And then in the constructive interference, you can really clearly see the global flame response high as a result. This is a great paper, and they did a lot of really nice work. They used some theory from Nick Kumpsty, on basically flows from turbo machinery, like blade rows, which is essentially what a swirler is, to show in theory first that this should work. And then they actually measured it, and it was just super cool. And so this is an example of two different disturbances, right? You have the disturbance due to the velocity fluctuation, and then you have the disturbance due to the flame, right? This boundary condition effect here that results in a global destructive and constructive interference effect at different frequencies. So this was really nice. Another example of this was published in Nick Bunce's thesis, but never published in a paper, and it makes me super sad. So Nick realized, he saw these same effects, right? This fluctuating swirl number, this fluctuating flame angle, the vortex roll-up that was happening at the edge of the center body, and he was like, I'm not going to change the flow velocity. I'm going to change the convective delay by changing the length of the flame, or the location where the flame is stabilized relative to the source of my fluctuations, which is the swirler. And so here he's changing the convective delay physically by moving the flame, keeping everything else constant. And you can see these are the original geometry. This X is what's called the center of heat release. And you can see it gets moved out a little bit by changing the geometry the way that he did. And then he measured the flame transfer function. And lo and behold, you see a really clear change in in both the phase, at all the phases, and the location of the nodes and antinodes in the transfer function because of this change in convective delay. And so now we have two different disturbances that are moving relative to each other, but we've just offset them. In the case of Paul Police's work, we've offset them by changing, this convective velocity. In Nick's work, we changed them by just changing the location of the flame, and you get the same result, which was really, really nice. So this is good experimental confirmation in more realistic geometries, right? This industrial hardware flows like at 30 meters per second, and you can see this really clearly, which is very cool. Questions on that? All right. So hopefully through this, between our exploration of flame kinematics and our discussion of flame transfer functions, you can now see why flames respond the way they do both locally and globally, and connect those two together. There's not enough of this happening in the thermoacoustics community, and that was one of my big learning objectives for you all. And so I'm glad we've gone through that. Okay, so I've measured this flame transfer function. Now what do I do with it? Because anybody in here ever measured a flame transfer function? No? It takes forever. It takes a really long time to do a really nice measurement. And it's not the most exciting experiment. And so you better have a good reason for doing it. And so what do we do with it? So I want to show you an example using an open source tool that you can all play with if you'd like, of a very common way of using transfer functions, and these are called network models. So I'm taking all these images and these equations from an open source tool called Oscillations. This is just from their tool documentation. Oscillations was developed by a professor at Imperial named Amy Morgans, and she is a brilliant thermoacoustician and control theorist who's done some really nice work, and also just a great scientific citizen by making Oscillations open source. So you can download this. It's a pretty powerful tool for a little program like this, and you can learn a lot. So basically what Oscillations does is you create a combustor geometry as a set of modules. So every time there's an area change or a flame, you basically make a different chunk. So it's sort of like acoustic Legos, and you put together chunk by chunk what your experiment looks like with the correct diameters and lengths. And then what the solver does is it knows in every module there's a forward traveling wave and a backward traveling wave. And then it just applies boundary conditions to the forward traveling wave and the backward traveling wave by conserving momentum and energy, mass, momentum, and energy at each of the interfaces. It's actually pretty clever. So this is basically, these equations are saying, okay, each of the variables I want to solve for, which is pressure, acoustic velocity, and density, I can do a Reynolds decomposition, so I have a mean and a fluctuating, and that fluctuating can be broken into a forward traveling and a backward traveling component. In the density, I also have this term that can come from energy addition, which, you know, is from the flame. So at each of the interfaces, you just start conserving stuff. So this is mass conservation, this is momentum conservation, this is energy conservation, and then you've got your equations of state and your definition of enthalpy. So I guess it's technically enthalpy conservation, but whatever, it's the same basic idea. And you can see that in the energy conservation equation, there can be a source term. And what you do with your transfer function is you model this source term with your transfer function, right? So all of this is written in the time domain, but then the way Oscillations solves things is it just puts everything in the frequency domain, because that's what good acousticians do. It has a model for Q dot in the frequency domain, which is your flame transfer function, and, you know, solves the system and looks for the eigenvalues. And so the eigenvalues of the system are the resonant modes. And so those are going to be the cases or the frequencies where you have thermoacoustic oscillations. So this will give you, so what you get out of solving the eigenvector problem is you get a frequency, a growth rate, and a mode shape, which is kind of cool. I want to stress that there's a difference between a growth rate and an amplitude. Two things can have the same amplitudes but different growth rates, right? The growth rate is, it's a rate. It's just the slope of that H curve, right, as opposed to the limit cycle of that H curve. But, you know, it's still a good piece of information to know. Comes out of the math, you might as well look at it anyway. But really the useful thing are the resonant frequencies and the mode shapes that you get out of it. Every time we build an experiment or a thermoacoustic experiment in my lab, the first thing we do is we put it through Oscillations and play around with this just to see what we think we're going to get, what the modes look like, that sort of thing. There are a few different models for heat release rate for the flame transfer function in Oscillations. The very basic one is called the n-tau model, which is a very old but still kind of trusty way of modeling flame response. And if you just want a super quick first cut, use the n-tau model. But you can now put in, you know, curve fits of your own measured flame transfer functions in there and, you know, look at the response of your system, which is pretty awesome. So this is another fun thing to play around with if you're interested. Okay, cool. Any questions on this? Because now we are leaving flame response and we're going to move to what do we do about it? Okay. All right, instability control. So obviously this is bad, understatement of the day. So we really want to decrease the amplitude of the instability. The goal is not always to like completely make the Rayleigh index less than 0. All you got to do is make the driving less than the damping, and it's not a problem for your system, right? And so the way that you do that, actually, I think it's very instructive to go back to the Rayleigh index, which was an equation we talked about at the very beginning of yesterday, to like look at the different terms and be like, huh, how could I modify these to suppress the instability? So there are 4 things you can do. You can increase the damping so much that your Rayleigh index, even if it is positive, results in damping that's greater than driving. This is the brute force way. It works. We'll talk about how you do it. It's not a particularly elegant way of doing it, but this is how we do it most of the time because by far it is the cheapest way of doing it. And so we just put a lot of acoustic dampers on stuff. So that's one. You can dephase P prime and Q prime over the acoustic cycle. Some clever ways to do that. You can just change the acoustic mode. Some interesting ways to do that. And you can change the heat release rate spatial distribution, which, again, if you just move the flame, we saw this with the transfer functions, if you move the flame out of the way of the acoustic mode or relative to the acoustic mode, you can get a different response. Okay, so we're going to go through each of these individually and see sort of what do people do in real life. So let's start with increase the damping so that it suppresses the instability. In most devices, there are 2 different ways that we damp out instability, or 2 different dampers that we use. One's called a Helmholtz resonator, and one's called a quarter wave tube. A Helmholtz resonator is a Coke bottle. And so if you've ever blown over the top of a Coke bottle, you have created a Helmholtz resonance. Congratulations. So Helmholtz resonators have what's called a neck and then a volume. And the frequency is kind of interesting. This isn't like a longitudinal mode of the resonator, it's a bulk mode. And so you can see that the frequency is dependent on that neck, cross-sectional area, the volume, and the neck length. So basically what you're doing is you're kind of having the whole thing breathe. And the frequency at which it breathes depends on the geometry of that system. And so you can see Helmholtz resonators on actual devices. These are Siemens combustor cans. The head end of the can is up here. And so there would be like 12 cans around the engine. So this is for power generation gas turbines. And you'd have a set of fuel injectors. So flow in this would go from bottom to top. It's obviously not on the engine, right? These things right here are called crossfire tubes. So you don't necessarily have an igniter in all the cans. You typically only have it in like 2 of the cans. So you light 2 of the cans, and once they're on fire, it sort of sends some fire through the crossfire tubes, and you light the other cans on fire. So they're talking to each other acoustically, which is a very interesting problem. This is the transition piece, which is one of the noodliest parts of a gas turbine. If something's going to break because of an instability, it's going to be the transition piece, because this thing is hot as all get out, and you got to mechanically fix it to the turbine, which is also hot as all get out, and then there's a part of it that's spinning. It's a lot. But then you can see these things, and these are Helmholtz resonators. It's a little bit hard to see, but you can kind of see that they stand off from the can. And so there's a little neck and then a volume, and it's not, beer bottle shaped. It's a rectangular prism. And so they've got Helmholtz resonators around the back end of this just to like bring down the noise level inside. One of the challenges with this though is like this is a fixed shape. And so you've got a fixed frequency. I mean, if your speed of sound changes, your frequency changes a bit, but you've chosen a cross-sectional area, volume, and a neck length. And so you're kind of like married to that frequency. And you can change the frequency of a system by doing a bunch of different stuff. And so this is one of the challenges with these. This is called a passive control technique, because once you put it in, it's kind of like that frequency. One of the ways to get around that is to use what's called a quarter wave tube. Quarter wave tubes aren't as fancy. They're just a tube with a hard end. The resonant mode that sets up in here is a quarter wave. So the frequency is the speed of sound divided by 4 times the length of the tube. And that's it. The nice thing about quarter waves tubes is you can tune them. So, right, you could turn this into a piston, and so you could change the length of that tube. And so you could tune the quarter wave tube depending on the frequency or the resonant mode of the system. The resonant modes of particularly gas turbine combustors change. If you install a power generation engine in the summer, the installation team will come back in the winter and retune the engine because just being cold outside changes the frequencies of the engine. And then they'll probably come back next summer because enough will have changed, you know. So you got to tune this thing kind of continuously. And one of the things they're doing when they're tuning it is they're changing the settings of those quarter wave dampers to suppress any instabilities in operating modes that you want to run at. So these are 2 different passive ways of dealing with it. The other benefit, so any questions on acoustic dampers? Yeah.
Acoustic dampers, can you predict that a little when you install them proactively, or is it always a reactive?
It's a really good question. So the question is, do you put these in proactively, or do you have to retrofit afterwards once you found an instability for fun? And the answer is you really hope you can put it in proactively, right? So these haven't gone on an engine yet. What they probably did was a thermoacoustic model, tried to get rid of a frequency, just couldn't, and said, all right, let's just put a bunch of dampers on and that'll help. That's one of the nice things about these tunable dampers is you can assume there's going to be a problem, hope it's in the frequency range of the size of your damper tube, and then tune it afterwards. There will be thermoacoustic problems. You just don't want them to be too bad. And typically, you have some inkling that they're like what the frequencies are going to be and what operating conditions they're going to be through just like system level modeling and testing ahead of time. If you find a completely new mode when you install the engine, that is real bad news bears. It happens a lot. And so, you know, this is one of the things that can help. Not the only thing. We'll talk about other stuff too. Other questions? Yeah.
I don't quite understand how the damping part of it. Because it has a specific frequency, there's a destructive interference. That's what damping is.
Oh, yeah, sorry. I didn't talk about that. It sucks acoustic energy out. So if you're putting in so much energy into the acoustic field from the flame, if you're resonating another part of the system that has nothing to do with the flame, you're taking some of that acoustic energy out of the system and sort of spending it in that resonator. And so it sucks the acoustic energy out of the system and dampens or dissipates it in the resonator itself. Yeah, sorry about that. Thank you for asking that. Other questions? Okay, cool. So another thing that damps acoustics are plates with lots of holes in them. Has anybody ever gone to a recording studio? Are we not that cool? If you look at the walls of a recording studio, it'll just be a wall of perforated plate. It'll be metal with tiny little, or plastic with tiny little holes in it, and behind the tiny little holes will be foam. The foam obviously, absorbs sound if you've ever screamed into a pillow, which, we all have. That's one way. But the plate with the tiny little holes is also damping the sound. And the way that it does that is it's transferring energy from an acoustic mode to a vortical mode. So if you remember, we talked about Chewin-Kvasny yesterday. It's back. We said velocity fluctuations have 3 components, an acoustic, a vortical, and an entropic. And we said in free space, these do not linearly interact. At boundaries, however, they can linearly interact, and that's good for soundproofing, because what happens is when you force air through a tiny hole with a dilative, like acoustic expansion, the separation off the edge of the tiny hole takes some of that acoustic dilative energy and turns it into rotational vortical energy. And so you dissipate some of that sound energy into vorticity. And vorticity doesn't make any sound because it's dilative. It's rotational, but non-dilative. So that's cool. And this was actually, so this is a really nice paper by Hughes and Dowling. Ann Dowling is like a hero of mine. She's a world-famous thermoacoustician and aeroacoustician, retired professor from Cambridge University. She did some really, really foundational work on both thermoacoustics and on acoustics. And this is a paper inspired by thermoacoustics, but looking at the damping mechanisms in perforated plates. And if you look at old school combustors, before we had lean premix combustion, they were just filled with holes, right? You had dilution holes all over the place. This is a Rolls-Royce turbojet. This is a P&W JT90, which I think was certified in like 1972, right? These are big. Look at that fuel injector. There's no premixing. This is just a massive fuel of jet of liquid fuel that then goes into a big combustor where there are a ton of dilution holes trying to get all that fuel to burn out. And so combustors weren't all that unstable because we had a bunch of holes in them. There's a really famous quote from a book by Putnam, which is on combustion instability, that says, if you have a combustion instability problem, drill a hole. If you still have one, drill another hole. And that's like, it's actually pretty good advice. The problem is that we stopped making combustors that look like this because they also made a crazy amount of NOx. And so if you look at a modern combustor liner, so this is a Siemens Westinghouse gas, they call it a basket, but it's the liner of the combustor. So now this is looking up that same type of combustor we saw before. There's a few, you've got the crossfire tubes and you've got some dilution jets, but this thing is just a solid piece of sheet metal with a nice thermal barrier coating on it. You've got many fewer holes. So not only did you, by creating a lean premix flame, make the flame much more susceptible to instability because you're running at really lean equivalence ratios near the edge of blowout and that flame's not happy, but then you took away all the damping by taking out all the holes. And so you really shot yourself in both feet, which is why most of us who do thermoacoustic instabilities work in gas turbines, because it's a huge problem for power generation machines. Okay, so that's damping. Questions on acoustic damping? This is what's called passive control, or one flavor of passive control. You'll see these dampers on a lot of machines. Okay, cool. So we can do that. But there, like I said, there's some drawbacks, and maybe it doesn't suck out all the energy that you want it to, so let's keep trying other stuff. So the next thing we're going to talk about is changing the heat release rate, spatial distribution, right? If I move the flame away from that pressure antinode, that would be great. And so there are a few different examples of that in machines. And I just keep using gas turbine examples because that's where I'm from. But you know, you can apply these general philosophies to any type of device. So the first example, again, Siemens is getting a lot of love, but they have actually published a lot of results, which not every company does. And so this is a really nice set of papers on suppression of instabilities in the X4 combustor. So not all Siemens combustors are cans. The Siemens Westinghouse ones are, but the just Siemens ones are annular combustors. So you've got this annular passage that goes around before the turbine. This is a dude in the annular passage. You can see how big these things are, right? These machines are massive. These are the fuel injectors, and then you've got the liner here is a bunch of plates, and you've got this dome plate here. As we'll talk about a little bit later, one of the types of modes, acoustic modes that can show up is not just the longitudinal mode, but the circumferential mode. And so one of the ways that you can suppress a circumferential mode is by introducing asymmetry into the system, into just the geometry of the system. This is a process called symmetry breaking. And if you are not symmetrically feeding the acoustic mode heat release rate energy around the annulus, you basically decrease the Rayleigh index, right? So if you can break the symmetry, because acoustics love symmetry, then you can really decouple this mode. It looks a little bit different for circumferential modes. We'll look at some pictures of that in a bit, but this picture's gold. Like, man, I wish more companies showed stuff like this. This is their injector, and you can see, like, this guy, all the injectors are a little tilty, and they're all tilted in different directions. So this one's tilted out of the page, this one's tilted into the page, and they had these at all different angles, and this symmetry breaking did a lot to suppress the instability, which is really, really interesting. What's the drawback? Why would we maybe not want to do this? Anybody have any ideas?
Because it's more expensive to produce.
Yeah, so there's some maintenance stuff, that's true. What else? What's called your pattern factor, which is the temperature distribution going from the combustor into the turbine, which is all the turbine cares about, is going to look wonky. And so if you have a nice symmetric pattern factor, right, the turbine has got 92 blades around it or whatever, and they want kind of a nice, predictable, repeatable thing going on. But now you've got these things all in different directions, and so you have to be a little bit more clever about how you inject air and do some of the dilution cooling downstream so that your turbine heat transfer people don't hate you. But it worked. Like, this is in operation. So you just have to be clever about how you do the overall combustor design. So this is cool, right? So now, no acoustic damping. We just changed the shape of the flame, and this helped suppress coupling with the azimuthal mode. Another example of this comes from my group. This is an injector from solar turbines, and they're not the only people that do this. There are a bunch of other ones, but their injector not only has a swirling flow, but it has what's called a pilot flame. This is a central pilot flame. Some injectors, GE has injectors where they have ring pilots around the outside, but you can put in this secondary flame. This is just a cell phone picture of the experiment, but this is the main flame. This is some RTV on fire. And then this is the pilot flame in the middle. And by changing the pilot flame, you're changing the heat release rate distribution and also how you support the main flame. So there was some work that was done by Ji-Hung Lee, who was one of Dom Santovica's last, I think he was Dom's last student. And he produced this absolutely beautiful data. So this is the pressure, normalized pressure fluctuation as a function of the mass flow of the pilot. And he sort of changed some stuff upstream so that he could independently change the mass flow of the pilot and the equivalence ratio of the pilot as compared to the equivalence ratio of the main flame. So he kept the equivalence ratio of the main flame at 0.6, and pilots that were richer decreased the instability amplitude. Pilots that were leaner made it much worse, which was interesting. And one of the big findings out of this, you know, a lot of people are like, I don't really want a rich pilot because that's just a NOx factory. You don't need a whole lot of pilot flow in order to really suppress the instability. And so this was a beautiful data set that Ji-Hung published. And then my colleague Yuan Schwan and I picked it up. And Yuan does a lot of simulations. And we looked in simulation at a bunch of these different conditions and looked at the mechanism by which the pilot is doing this. And so these are a cut of the center line. What I want you to look at is the picture down here. This is temperature. And so this is with one of those leaner pilots. It's kind of cold in here. This was with a richer pilot. And that richer pilot basically back supports the main flame and makes it a lot stronger, makes it a little bit tighter. and so it's less susceptible to instability as a result. So we changed the heat release distribution a bit. We sort of changed the strength and geometry of the flame, and we can really suppress the instability as a result. And this is one reason that people use piloting. Another common way of doing this is called fuel staging. And so piloting, you can vary the equivalence ratio between multiple circuits in a single injector. But fuel staging is where you change the equivalence ratio from injector to injector. And so this is a GEF class engine. And if you look at each of these cans, the head end looks like this. It's called a 5-around-1 configuration. You have 5 nozzles around a center nozzle. And typically, these have 3 different fuel circuits, PM1, PM2, PM3. And you can see how they're broken up here. This is the DLN 2.6 is the type of combustor geometry. We have a similar experiment in my lab, and I'll show you what it looks like in just a second. But by redistributing the fuel between nozzles, keeping the global equivalence ratio constant, you can really suppress the instability. So the blue, so this is how we define stability. This line is kind of arbitrary. The blue is all nozzles fueled equally. And so at equivalence ratios approaching 0.7, this thing screams. And it's really loud. You'll see a picture of it in a second. It's like 115 decibels in the room. It is intense. If we take 1.4% of the fuel and we put it in the middle and we take it from the outsides, it has some effect. But 4.4% of the fuel, you can completely suppress the instability. So the global equivalence ratio is constant, so the power from the machine should be constant-ish. But just by redistributing less than 5%, we can completely suppress the instability, which is pretty impressive. Okay, so what's the experiment we use this on? So this is the facility in my lab. It's a 4-around-1 combustor. We wanted it to be symmetric so that we could do some cool imaging. This was built by Dom Sandvika, and then I inherited it, and like my first big project, he and I worked together on this. And we put in the staging fuel. Eventually, we put it in all the different nozzles to look at non-axis symmetry effects. But the data I'm going to show you takes the fuel out of the outer nozzles and puts it in the center nozzle. Uh-oh. There we go. So this is what it looks like and sounds like in real life. So you hear that sort of 520 hertz tone at the top. There's just a lot of turbulent noise because this thing is huge. But then that tone is the instability frequency, and then you can see that center flame gets a little bit brighter. We've staged the center, and you don't hear the tone anymore, which is pretty cool. And so we did a lot of imaging. This is actually a video of local phase between heat release rate oscillation and pressure. And one of the things we found, if you watch this video enough times, is that we could see the different nozzles as we were staging go out of phase with each other temporarily before there's no instability, and so the phase doesn't mean anything. And so we were like, we should look at these flame edges more closely. You can see here that we were staging this flame. This guy's still really strong, and then over here it gets a little bit wonky, right? And so we looked at, we used a bunch of high resolution diagnostics to look at this more. And I wonder, of course the video is not going to play. There we go. We used a bunch of OH PLIF on 2, different flames. This is completely unstable. You can see the flame edge here and the flame edge here really going together with pretty large flame wrinkling, and they're oscillating coherently. Down here, this is stage stable. It's turbulent, but it's not chugging. And we could, because of a default in the manufacturing, we could actually get a case where it was kind of stable, but kind of not. And so we called this the metastable condition. And so it fluctuated in and out of instability, and so we could watch it as it did that. So this was a bad weld job that ended up really helping some science. And so if you look at these are the fluctuations of the flames. If they're out of phase, it means that the flames are fluctuating together because one's going left and one's going right, right? So these are really high amplitude, out of phase, everything's chugging together. Here, when everything is stable, they're fluctuating together. So they're canceling each other out, and you can see that start to happen in the metastable stage. So the paper that's at the bottom explains how we did this. But basically, we're redistributing the fuel, we're changing the dynamics of flames next to each other, and we're canceling out the Q prime by changing basically the shape of the flames locally. And this is pretty neat. Gas turbines do this all the time. Yeah?
I have one question. So what is L prime? Can you do that?
It's the lateral fluctuation of the flame.
So how does it relate to the unsteady frequency?
The same way it does here. Here, instead, we were looking at zeta prime. It's very hard to do in an experiment, so we do it from the center line. But it's the same thing. You look at the oscillation in the flame location, and you can correlate that to the oscillation in the heat release rate. So this is a really good example of how knowing theory helps you interpret your data. Because we would have never done this had I not worked with theoreticians for 5.5 years as a grad student. Okay. So, all right, so that's changing the heat release rate. The next option is just change the acoustic mode, right? Move the pressure antinode relative to the flame and see if you can just break up the acoustics relative to the heat release rate source. The most common way of doing this is baffles. We've seen baffles before, right? We saw the F1. And so this is how baffles were implemented in rockets. We saw this picture before. This is the LM6000, which is an aeroderivative GE engine based on the CF6 aircraft engine. This is a really nice paper. Actually, this was written by Håkon Mangia, or led by Håkon Mangia, and a guy, Tim Held, who's no longer at Håkon, retired years ago, but Tim went and joined a cool startup that does other stuff. But this is a chapter in that book that I brought yesterday, and it's just a really nice discussion of combustor design and how to design around instabilities. And so this is the cross-section of the combustor. And so in particular here, they were talking about the damper tube. But one of the other things you'll notice, they don't talk about this, but if you think about it and, do some inferencing, one of the other things that's probably also helping are these heat shields. These are essentially baffles. These are these circumferential baffles that you see on the rocket. And those help to break up modes that go transverse, particularly radially. I have gotten enough knowing looks from Tim Held that every once in a while these engines do face radial modes, and they're super high frequency and extremely destructive. And so I'm sure these heat shields really help with flame stabilization, right? You get really nice recirculation zones, and you can make a good argument about static stability at super low NOx levels, blah, blah, blah. But I have a feeling that these baffles are probably also really helping with acoustic mode suppression. So there's been some nice work on this from James Dawson. So I think this was done when James was at Cambridge, but he's now a professor at NTNU, as is Nick Worth, who's the other the other author here. The work that James and Nick do is just excellent. And so they have this cool experiment. They built it in Norway as well. It's an annular combustor. So you can see they've got all these tubes that feed the combustor. They've got a quartz liner And they can change a bunch of stuff. So they can change the number of injectors. They can change the amount of swirl in the injectors. And in this study, they changed the baffles. So they put in baffles in a bunch of different places. And then they have this big mirror on top so they can image chemiluminescence from the top. So they get these really nice pictures like this. And so this is one baffle. You can see the baffle here. This is two baffles, the symmetric, so one's here and one's here. And they basically looked at the forward and backward traveling wave amplitudes for a bunch of different operating conditions for different baffle positions. And down here, as you put in more baffles, the instability amplitude went down. And so this was pretty neat. You don't see a lot of baffles in operation in power generation gas turbines. They would burn up. There'd be a real maintenance issue there. But it is kind of a nice way to deal with this. And this study was a nice way of visualizing that. Okay, the final thing I'm going to talk about, and then we'll go into our next break, is about dephasing the pressure and heat release rate over an acoustic cycle. And the real way to do this is with active control. And so active control is really difficult. There are just a glut of theoretical and small experiment active control papers that all come to the same conclusion, like active control works. I don't know why we're not doing this. You know, beautiful control theory, and then, you know, simple experiment, what's going on. We just saw a combustor that a man could fit in. Where's that picture? Ah, I lost the man. Where is he? There he is. This is probably a 400 megawatt engine. Let's say on order of magnitude, it's 50% thermal efficient, which it's not. It's probably less. That's 1,000 megawatts of heat you're putting in. There's no actuator on Earth that's going to be able to control that level of heat release rate reliably over a long duration of time. It's not to say that people haven't done it. And this paper on the bottom left, the one with the guy, application of active control combustion instability in a heavy-duty gas turbine, they did this at Siemens, and it worked. But it was crazy expensive, and the actuators burnt up really quickly. So before anybody gets too excited about active control, let me burst your bubble now. But it's worth mentioning because it does work. So this was a study, again, from that same book. This is, I just keep using these industry case studies. This was one written by Jeff Cohen and Bill Proscia, who at the time were at Pratt & Whitney. Bill has retired, which is sad, and Jeff now works at the research center there. But anyway, they had a big NASA project where they were looking at active control and doing some neat stuff. So basically, they built a rig that had a similar instability to an engine they had. So you can see this is the frequency spectrum of the engine instability. This is the frequency spectrum of the rig. So we're like, close enough. And then they looked at different ways of active control. And the way that they did active control was they pulsed the fuel. And so you have a fuel inlet and a fuel outlet. And so some of your fuel is pulsing. So some of it comes in a steady stream and some of it pulses. They tried a bunch of different control algorithms to dephase P prime and Q prime by basically changing Q prime by feeding the fuel at a different phase. It did work. So this is open loop actuation where you just like pick a phase. But if you actually have like a nice model-based control feedback, then you can actually suppress the instability pretty well, which is great. So it works. It's just expensive and complicated and doesn't work as well as you would want it to. Okay, before we go to break, because we have 4 more minutes, because we didn't come back until 3:20 before, we're going to talk about a bonus suppression method. Everything I've talked about today so far in suppression methods are either commonly used on engines or well known enough that people have tried in the case of active control and decided it's not worth it. In my group, we're doing some work in collaboration with a very good friend of mine, Santosh Chandra, at the Indian Institute of Science in Bangalore, to look at a different way of controlling instability, which is, what if we didn't stop the feedback loop by changing the flame or the acoustics, but by changing the flow? And so in particular, what we are looking at is how do you break the coupling between acoustics and the velocity fluctuations that come from the acoustics by suppressing the receptivity of the flow field. And so instead of trying to change the flame location, damp out the acoustics, whatever, you basically just design a flow that doesn't respond to the acoustics, so you don't get any velocity fluctuations, so you don't get any flame fluctuations. We happened upon this accidentally. An undergrad researcher found something years ago during a summer research experience. I made him retake the data like 3 times because I thought it was wrong. And then it led to a series of really good papers and a large part of my symposium plenary 2 years ago. And so that's what I'm going to quickly go over now. In order to understand this, you do need to understand something on flow receptivity, which I don't expect people to know, so we're going to go over a quick example. Flow receptivity basically looks at how receptive or how unstable a flow is to an input perturbation. And so the easiest way to talk about unstable flow is to first talk about stable flow. So if you have a flow field, you walk upon a flow field, and you kick it, it'll oscillate, right? You throw a rock in a pond, and the pond gets ripples, but then they die out. And so if I waited long enough, the flow would just go back. This is a stable flow. Some flows are what we call disturbance amplifiers, where I come upon a flow, and I kick it, and it responds, and the disturbance gets bigger as it convects away, right? For those in the know, these are called convective instabilities, and they amplify disturbances in space, but then over time, it would just go back to normal. If I kicked it again, it would do this again, or if I continually kicked it, like hit it with an acoustic field, I'd get an amplification of that input, but it's not going to do it on its own. Then there are the flows that do it on their own. These are called self-excited flows or globally unstable flows. And those, you happen upon the flow, and it's already oscillating. It's doing it all by itself. One should ask, what happens when you kick it? And the answer is, it's complicated. There are a lot of different options. And if you're interested in this, there's a recording of my symposium lecture that spends 20 minutes on this shruggy emoji and the answer to that question. Okay. So what we're trying to do is look at flows that are disturbance amplifiers and stop them, change the flow so they no longer amplify disturbances, which we found was possible by mistake. So the most recent work where we looked at this was actually in a pretty realistic combustor geometry. This was data that was taken at DLR Stuttgart by Isaac Fox. And this is a dual swirl injector. So you have an outer passage and an inner passage. Ethylene fuel is injected in the middle. So this green is fuel pliff, and the red is OH pliff. So you can see where the flame is and where the fuel meets the flame. So it's partially premixed. This is pretty representative of a lot of particularly aircraft engine injector geometries. So what we did, well, what Isaac did, and then sent us a whole bunch of data because he didn't have time to process it all himself, and we're friends, was he changed the air split. So from no flow through the center to all the flow through the center in the non-reacting case, and then in the reacting case, some of the flow through the center to more of the flow through the center. It was at pressure of 5 atmospheres, pretty high Reynolds number, whatever. So looking at the non-reacting data, as you put, this is no flow through the center, this is all the flow through the center, you can see this big recirculation zone starts to form. You get a much tighter swirling flow, much stronger swirl because of the way that this is set up. And what ends up happening, if you do a bunch of analysis, is you get a global instability called a precessing vortex core that shows up in the middle. And anybody who works in swirling flows, precessing vortex cores are like so hot right now, and everybody does PVC work. There are only like 4 people who I think genuinely care about it, and a lot of people misdiagnose precessing vortex cores, but that's not a soapbox I'm going to get on today. But anyway, so when this is non-reacting, this thing, like at these higher air splits, just screams. It's got its own globally unstable flow. It's kind of exciting. In the reacting conditions, same kind of thing happens. As we increase the air split, you get more recirculation in the center. The flow is like, wider and more diffuse because we've got all that heat release. And now we've got like a bunch of modes. This combustor has 2 different thermoacoustic modes that are coupling with 2 different acoustic modes in the system. So that was fun. There was an interaction mode, and at certain air splits, we still saw the PVC. It was bonkers. But what we saw was we tracked the mode amplitude, and what we saw was as the precessing vortex core got stronger, the thermoacoustic modes got way weaker, which was very interesting. And this is something we had seen in my lab years before in non-reacting cases. We had seen the receptivity of the flow to external acoustics just nosedive when you got a PVC. But we said, we don't know if this is going to happen in experiment. There was some work done at TU Berlin that suggested it could happen. And then we saw it like in the wild in this experiment, which was a lot of fun. So then Santos's group did what they do best and showed using nonlinear theory. That top equation is the Navier-Stokes equations, in case you couldn't recognize it, with a bunch of forcing terms on the right. You do a 2 timescale expansion, and basically what comes out is this really important term. This is the oscillation amplitude of the thermoacoustics, which is dependent on the interaction between this hydrodynamic mode and the thermoacoustic mode. And so we could show in theory, I'm not going to go through all the math, we could show in theory why this was suppressing it. And this would be like a 3rd way of doing instability suppression by doing some fancy fluid mechanics. This is published in the Journal of Fluid Mechanics. It's open access, and it's some of, I think, the coolest work we've done together. This is a really fun project. Okay, so with that, we have learned all our learning objectives. We have identified technologies in which combustion instability occurs. We've talked about the basic coupling process. We've played a lot with our pipe cleaners and straws and hopefully have a much better appreciation for the kinematics of flame response. We've assessed flame transfer functions, and hopefully now you can use your pipe cleaners and straws to explain why flame transfer functions look the way they do. And now we've used what we know about thermoacoustic feedback to understand why certain suppression mechanisms work, and learned about a bonus one because it's something I'm interested in as well. So I went 4 minutes over, but at this point we'll take our break and then we'll come back and we're going to talk about 3 what I'll call advanced topics: transverse modes, nonlinear instability, and entropy coupling, or what's called indirect noise. But I'm going to go through those pretty quickly, and I want to leave some time for things that you want to talk about. And so if you have things you want to talk about, maybe come up and tell me now so I can like cogitate a little bit as we're drinking coffee. Or you can come up with them on the fly and we'll just see how I do. But let's come back at 4:40 and we'll close out the end of this.